I'm going to unscale it for you. I'm just going to write the numbers that would normally be there. So basically, what you would have is on the design, you see the three sections. Here's the section for Q is equal to 1.618. Here's a section for Q is equal to 1.618. And here's a section for Q is equal to 0.5. Okay? So we were to start this design from nothing, just assuming omega naught is equal to 1. Okay? You would have this resistor at 1 ohm. Okay? In fact, every resistor would be 1 ohm. So what I'm going to do is I'm going to cut all these out, start from scratch, to show you what you expect as you go through different stages of the analysis. Okay? These are all going to be 1 ohm. In fact, this resistor is going to be, this capacitor will be 1 farad as well. Okay? This 1, 1, this gives you the whole minus 1, right? I'm going to do a completely unscaled design. The only thing to change in these two designs, or in these two circuits, is the value of Q. Okay? So that capacitor is going to be 2 times Q. This is going to be 1 over 2Q. And as you can see, this is for using Q is equal to 0.618. By the way, I can come down here to define a parameter called Q1, Q2, and just put down 2Q2, 1. But I just left it there for you to see that's the number. Okay, so I'm going to go back, and I'm going to get rid of all these scaling factors. So that capacitor is going to have a value of 2 times 0.618, and this is going to value 1 over. Okay, so this is the stage right here. Omega naught equal to 1, and Q is equal to 0.618 in design. And that design is K equals to 1, right? Capacitors are unequal, but that's the way it is. In the second stage, same thing, but now the Q is okay 1.618, and this is also the same. So one is 2 times, one is 1 over 2. So now this design is set. This will give you the right attenuation characteristics, assuming omega naught is equal to 1. Now, here's an aside. So far, we're dealing with frequency in hertz. If you want to plot things in radians per second in LT spice, you really can't do it directly. So what you have to do is, you have to first declare a parameter. In this case, I declare a parameter W, which is your omega. And it's going to go, in this case, it's not the right range, but anyway, it basically defines a parameter omega W. Starts from 10 radians per second, goes to 10,000 radians per second, and it picks 100 points per decade. This is the decade definition. So it basically generates a list of numbers. It's like defining a variable in MATLAB. You're defining a vector, right? That's all this is doing. Now, when you feed information into LT spice, you have to report in terms of hertz, right? So when I do the EC analysis, it's going to be based on a list. Okay, so it's going to run AC analysis for a list of frequencies in hertz, and those are just the W, the omega, divided by 2 pi. Okay, so I declare omegas, but I feed in, hertz, frequency in hertz. That's the way you do it. Okay, now remember, if I just run the simulation, I'm not going to see anything because everything interesting is happening around 1 radian per second, and I'm not even around that range. Because this was for the scale design, right? So, I can just run it and see nothing. Okay. Well, first of all, let me get rid of the here. There's that one. I don't want it to automatically give me the plots because I want to show you what happens. Okay, so if you run this, okay, you're right, no problem. If I go to the output here, okay, if I plot this V out, this will give me the what? The gain, right? V out over V in. Okay, and you see it gave me the phase too. I don't want the phase, so I go with my cursor here, go to a ruler, click it, don't plot phase. Now, this doesn't look like a low-pass filter, but actually it is, right? The problem is that the horizontal is not a log. Horizontal is linear, you see that? So what you got to do is, again, take your cursor, bring it here, turns into a ruler, left click, logarithmic. going on here is that you're way out of the range of this frequency, so you're not seeing anything, all right? You should really be plotting it around 1 radian per second. Okay? So let's plot it for 1 radian per second, around 1 radian per second. I go here, and I can just right-click here. Okay, I'll put it up. So I just right-click here. I can say, start at, let's say, 2 decades below, at 0.01, and go to 2 decades above, 100. Still take 100 points per decade. Okay, and rerun the simulation. Okay. Now I see like a low pass, right? But remember, this is the gain, right? This is like V out over V in. Although I'm not plotting V out over V in, that's what it's giving me. Because if I go here, and I mentioned this before, but I'll just show you. If I just go here with the cursor, right click, okay, instead of V out, if I plot V out divided by V in, what it's basically giving me here is 20 log magnitude V out over V in. That's what it's going to give me. But V in is 1 at 0, right? It's a phasor. Has a magnitude of 1, phase of 0. It's not going to change anything. Doesn't change anything. Okay? Now, if you want to plot attenuation, you got to plot 1 over this. So you can do 1 over this whole thing if you like. Or you can do V in over V out. But if you do V in over V out, some people get confused. Is the input now here? No. Okay, it's not. But if you right click here, if you just do 1 divided by that whole thing, like this, you'll get it. That's the attenuation now. I know this is a little dark, so yeah, just turn this off. There was no. Turn off all the lights. Don't get scared, okay? I'm still here. Alright, so I mean, you can see much better now. But this is attenuation, and you can say, oh look, this is 1, right? And everything is normalized to 1, so this is where you expect your 3 dB point to be. So is this 3 dB? Well, hopefully it is, otherwise I've done something wrong. So I go here, zoom in, and you can put the little cursor on. Here's the cursor, and move the cursor until you see horizontal 1, and you should see about 3 dB here. Remember, that's attenuation, right? So that's the reduction. Alright, so if you move it to around 1, maybe right there, you see about 3 dB. So I know that this is correct. The design is centered at that point. Now, that's not where I want it. I want it at 1234. Because if I make it at 1234, I know that my omega P and omega S will be in the right places for the design. Okay? So what I'm going to do is, I'm going to go back, and I have to frequency scale. Divide all the caps by KF. And here I have conveniently listed KF, 1234.12, as a parameter. So all I got to do is go to those caps, divide every cap value by KF. So I can do that. Go up here, right click, and keep doing this thing, divide by KF. Okay. Or you can put the actual value there if you like. So divide the whole thing by KF. Okay. Or I could have done, I could have put the KF inside the parentheses, times KF, 1 over the 1. But you can just divide by KF. Alright. So I gotta do 3 more capacitors. Okay, 1 here. Divide this by KF. So when I do this, the entire thing should shift from 1 radian per second, okay, to 1234 radians per second. Okay. My last but not least is this one. Sometimes people forget this, and it's a common error. So don't forget that one. Okay. If you do this, okay, rerun the simulation as is, you're not going to see much because now you're not in the right frequency range. But let's just do it to see if it runs. Okay, hopefully it'll run. Okay, it ran, but you don't see anything happening because things are happening now way down the line at 1234, not at 1. At 1, it's nothing. Okay, so you have to simulate